Okay, so if you look at the syllabus, next week in lab, we're supposed to have our test one. I want to put that back so you can hand in this homework and get it graded and stuff like that, and get a little more experience here. So the test one is postponed by a week. Let's see, Monday was the 7th, so add 7th, so that'd be the 14th, right? It's postponed by a week, so it is.
Yeah, 2 exams on 14th.
Not Friday. Yeah. Monday. February 14th.
So Monday.
That's what it's scheduled for.
It is? Okay.
Yeah.
Well, that's what I can do since I'm using this superior technology called marker.
Okay. Have you moved?
And then homework 3 is due. And as far as the class goes, the test goes, it'll be just like we did last year. The test will be during lab. So the test will be during. I have 2 lab sections, 121 and a 321. You're welcome to start the test during the 121. And you can stay through the 321 or whatever. I'll stay a little bit past 5:10, not a whole lot past 5:10. I'm going to tell my wife if she wants me home. So if you think you need a lot of extra time, come early, and then that's perfectly fine. I designed the test to take an hour. It'll usually, it's been my experience, most people take about an hour and a half for it. They finish a little bit around an hour, but then there's like this half-hour period where you have to have enough confidence to hand it in, and so that takes a little while. I will also hand out the exam I gave the previous semester, which is actually quite some time ago. So, I don't know, I'm gonna have to check. So I'll find out what every test I gave before. I'll print that out and I'll give you a copy of that so you can see the type of things I give. For those of you who had me in 125, you know it's the exact same format. How the test will go, there's 2 parts, which I call part 1 and part 2, kind of clever. Okay. With part 1, there's going to be 6 questions. Do I need 5? Okay, you can do the 6th one as a bonus. So the 6th question, okay, is a bonus. So you have 6 questions there. Choose any 5 you want to do. Those ones will be graded. If you want to do a remaining one, you can. Okay, now this is just test strategy. If somebody is giving you a bonus question, what do? You do it. You know, even if you just read a poem, it's better than just leaving it blank. Okay. So try to do this. The part 1 here, these are going to be shorter questions.
Not as long? Or
Yeah, meaning just kind of like one part. Maybe it'll be something all self-contained. A part 2 here, these will be 3 longer questions. You do all 3. And these will have multiple parts. Okay. For example, what do you think these questions are going to be? You can pretty much already tell what it's going to have to be here. Tell me what 2 of those questions are going to have to be. One is going to be an extended Gauss's law question. Okay. What do you think another one's going to be? Yeah, something where you're going to have some form of expansion on there, something where you're going to have to integrate over something like this. Okay, so you already know what 2 of the questions have to be. Okay, can't wait to find out what the 3rd question is going to be. I hope it's interesting.
What do you mean? What's the second type you just said?
Just longer.
No, you just.
We have to have something you have to integrate over.
Oh,
You find the electric code.
how did
But you already know what those things have to be. What are the only things I can have you easily integrate over? Mm, a ring, then going to the disk, and then a rod. So there's not a lot, and again, there's a reason why there can't be a lot of variation on this. Because basically, if you do any variation on this, it becomes pathological. I mean, really, really hard. Okay, so at this level, there's not a, it's very constrained what I can actually give you. Okay, so what I'll do, I'll skip every other word in the problem to make it a little more challenging. Okay, and then I'll try to write the question to be very vague and obtuse, so it doesn't make a lot of sense. So there'd be things like, you know, that term with the charge? Yeah, wow. Let's explain that term. So that'd be like that. No, I'm kidding. Okay, questions with that? Okay. There'll be a word search. There'll be connect the dots. You connect the dots, it's gonna form an equation, you have to figure out which one it is.
What would be a restaurant menu? Where you have to like solve the cipher.
Yeah, there'll be something like this.
You gotta hold the paper to a plane to read the question.
Figure out what this is. Okay, that'll be like one of the longer questions. Okay. So, and it has to be what I'm thinking, not something that fits. It has to be exactly what I'm
The
thinking.
word or O and the letter R. It doesn't even say where, it's just what's in your head.
And as I told you, what there won't be an equation sheet, but what I will do is on the back, there will basically be a lot of symbols. So on the back, what I'll do is I'll give you a whole bunch of symbols like this.
You got a piece in the head.
Yeah.
So we spread in the library for it.
So there'll be something like that, and that'll be Gauss's law. And you can see that because if you circle like that, this is this guy here. Okay. Then if you do like this part here, and you go here, here, then back over here, then back over here, that's obviously E dot dA. Okay.
Yeah.
Then if you do the E on C here like this, and go to the Q, the equal sign, that's the equals Q on C. Oh, God. This is obviously the next one up, which then goes to this one here. Okay. And so that'll be, this is how the equation will be. Okay. It'll help you read them. It'll help you think. Okay. And there'll be like, 12 pages of that for all the equations. Okay. Okay. So I got you covered. Trying to help. But I also like to stand over you periodically and then make noises while you write the test, like, "Ah!" That'll help you concentrate. And say things like, well, if you think so. Sure. Probably true. Okay. Let's try another example here. Let's say we're going to have a hollow sphere. This is a non-conducting sphere. There's a point charge in the center, so this is going to be +5 Q in the center. Non-conducting sphere of inner radius A, outer radius B, with a +5 Q point charge in the center.
Is it uniformly
I
charged?
can't wait to find out.
Oh, yeah.
The charge density is R squared.
That's a +5 Q.
Yep. What do you think the part A of this question is going to be?
Find E area.
Find E everywhere. Okay. So how do now this would be like a part 2 type question, I would expect. So how do you know how to proceed? I'm asking for an electric field.
We see a sphere.
And we see a sphere.
Gauss.
So it has to be Gauss's law. Why is it Gauss's law?
One of the geometries.
One of the 3 geometries we have. Okay.
Is the sphere, does the sphere have a net charge of 0? Yeah.
Does have net charge of 0.
No. Well, but by the problem, does it have a charge?
You tell me.
I'm asking if you, I know you know what I'm asking.
Yes, I do. Given this here, what does the
Oh,
answer have to be?
okay, now I see.
Okay, so it has to be a Gauss's law problem. So when you do these Gauss's law problems, what do? Where do you start? inward, and go outward. And the first thing you're going to do is
Draw Gaussian surface.
draw Gaussian surface. Okay, so how many regions do we have?
3.
Yeah, so we have 3 regions here. You have R less than A. Here. Here. And always start inside and work out. So, can I say Q enclosed equals 0, therefore there's no electric field in the hole?
No,
That's what happened in lab.
but it's not 0.
Correct.
There's a 5Q charge.
Yeah, well, now we have a charge in the center. Okay, so what do we have? So in this case here, here's our A. Here's our 5Q. I draw my little Gaussian surface like this. Right, here's my B. Draw my little Gaussian surface of radius R. We write Gauss's law.
Do we have to go through Gauss's law again?
Okay, what would be the fast way to do it?
It's a point charge.
It's a point charge, so what does it have to be?
KQ squared.
Take Q over R squared, or Q is
The Q equals
Which is?
5Q.
the 5Q. Okay, so we know that this answer here has to be, this is a point charge. So we know that this has to be E equals K 5Q over R squared. Let's just do this just actually for no reason. Okay, so what do?
We draw E's and DA's.
Yeah, so you go over here to our favorite little spot. It happens to be right here. If I'm right here, how does the dA vector go? It has to go outward and normal. E has to go out like this. Okay. Then what happens to my little friend here? Oh, it's not going to be detailed Monday. Okay.
It's going to be E by the integral of dA.
This is going to be 1. Again, why can't I take out the E again?
It's constant on the Gaussian surface.
Constant on the Gaussian surface. Does that make sense? Okay, so you can take this out. Oh, there's also going to be interpretive dance on the test too. Over like that. And that's obviously what that is basically point charge.
Okay.
If I go like that, that's flux. Okay, don't confuse the two.
Okay.
So also there's going to be basically, I'm going to say that is Gauss's law, and is then integrate over it. Then you have to figure out what I'm asking. That one. Okay, so what does this become?
Can we have notes for this?
Turns
Anybody
out you
taking
can.
notes?
It turns out you can.
E times 4
Yeah, if you take a little dA here and someone bump over an entire surface of the sphere, you get the surface area. And this has equal to charge enclosed. So what's your charge enclosed? 5Q. Divide that by epsilon naught. So that gives me the electric field equals 5Q over 4 pi epsilon naught. That's good. Why does it look different from what we guessed?
Because
1 over 4 pi epsilon naught is K.
Yeah, 1 over 4 pi epsilon naught is from K. Does that make sense? Okay. Done. Let's do the next one. I want a bigger picture. Come over here like that. Surface. And what does this side here have to be?
again, E magnitude of E by 4 pi r squared.
Yeah, this has to be the same thing as before. That doesn't change.
Still.
Now, where is a charge enclosed if hard to say shaded then?
Second circle from the outside.
Yeah, it's gonna be all the charge here. Is there any other charge?
In the middle. So there's gonna be 5Q plus all the charge in the sphere.
Yeah, so you're gonna basically have the charge here from basically the sphere. Plus the 5Q over epsilon naught. This entire combination here is your charge enclosed. Does that make sense? Okay. So now let's figure out how to find the charging close. Okay, how do we find the charging close?
You integrate. You take a DQ.
You have to add row.
So we know that
How do we incorporate rho? Why can't I just take rho times in the volume of this?
it's not constant.
It's not constant. So what's our trick for doing this?
We want to consider like one sphere as DQ, one charge, small charge as DQ over dV.
Think through what you're saying. If we come out here some distance, and what do we call that distance? We're calling it R prime in lab, so I'll keep that same much as R prime. And then we know that our charge density is this R squared. Okay. So the charge density right here at this point here is R prime squared.
Yeah.
Where else in this picture do we have the exact same value of rho? Any sphere like this. Now, rho is a what?
Constant index.
Charge over.
Charge per volume. We don't have a volume yet, so what do we have to give this? We have to give this a thickness, which we call dr prime. This right here is dr prime. I'm going to shade this in and make it look pretty. Okay, so now I can actually write the rho for this here. I can say that the rho for this is going to be the charge. So this is again, this is basically like a balloon, or you can think of it as a soap bubble. Okay, or an onion layer. Pick your favorite thing. The main thing is that it has a very, very thin thickness here. So basically, this is so thin that basically the radius through this is all the same R prime. So it's a constant here. So if it's a constant in that shell, how can you now write it? What's the charge in that shell? DQ. Now we need the volume of the onion layer, or the soap bubble, or the balloon. So what would be the thickness?
dr prime.
Okay, dr prime, then times your surface area, that would be the volume. So we take the surface area, 4 pi r prime squared. So that's the surface area of the sphere. Then if you multiply it by the thickness dr prime, that then is the whole volume of the onion layer. Does that make sense?
Yeah.
Okay. Then we equate this to r prime squared. I take everything over here, and this gives me dq equals 4 pi r prime to the 4th. So that's the charge in this little onion. If I want the total charge from that sphere, where do I have to sum these up?
From 0 to
No.
from A,
Why can't we go from 0 to r?
because this is the charge of.
Yeah, there's a hole here. So these onion layers start at a radius of little a, or just of a, and then they're going to go up to a value of little y. Okay. Does that make sense? Right.
Where did the initial, like, I think it's the, I don't know, that's all top left corner. Where did that come from?
I just made it up.
No, I know it comes from that one, but where was it? What do you mean you just made that?
Oh, I just said it has a charge density that's varying. So I just said this.
Okay.
You'd have to be give that information. Okay. I just wanted something that was varying. Okay, so then if I want the charge of the sphere, it's going to be the sum of all these little DQs. This gives me
Where did the R prime squared come in the bottom of the row term?
this guy here. So that's the surface area of the sphere. Okay. So in other words, this guy here, that's the surface area. But here, take the surface area and times your thickness. That's not the volume.
Okay.
That makes sense. So then this gives us the 4 pi r prime to the 4th dr prime, and then what are the limits of integration here?
From A.
A to R prime. Oh, R.
Okay. So this gives me 4 pi r prime to the 5th over 5 and r. So this gives me 4 pi over 5. R to the 5th. Let's see. That's our Q. I'm the Q this. So if you want the total charge enclosed, you have to add this to that 5Q. Yes.
Why did you set that equal to our prime
Okay, which one?
lower by one, up one,
This guy?
yes.
Okay, so a rho is by definition is your charge. Unit volume. And I said that the rho here, I just said is, I made this up here. Okay, so if you're right here at this value here, the radius for this one here is r prime. Okay, so I just put in the r prime. Does that make sense? Okay, so are you happy with this ratio here? Okay, now we have a charge density for the system here, and I told you that it's r squared here. And r is just your radius here. So what's the radius of this circle?
Here.
No, that's the thickness. What's the, right, because it's really, really thin. So what's the radius of this?
R prime.
R prime. So all I have to do is the r then is r prime. Okay, so I put the r prime here because that happens to be the radius for the circle. That makes sense? Okay. So we get this. Everyone happy with that? Okay, so what we do if we put it all together. We get 4 pi over 5. R to the 5th. Say to the 5th. Plus 5q. All over epsilon naught. Okay. So then if I solve for this, I get E equals. I get two terms here. I think I'll write it as two separate terms here. I get this as r to the 5th minus a to the 5th over 5 epsilon naught r squared, and then plus. I'm just splitting out the two. Does that make sense? Why would I split it up? You don't have to do that. You could just divide this by 4 pi r squared and you're fine.
So you could simplify it.
No? Okay. What would be the advantage of this? What does this term have to be and what does this one have to be? Interpret this. This term is the electric field at this spot
Due to the charge.
due to our point charge. What has this piece to be? That's going to be the electric field due to the actual sphere.
Yeah.
That makes sense? Questions on that? Okay, what do you think your chances of seeing something like this on the examiner?
Very high.
Yeah, it turns out my cats really like these problems. So that's... I mean, my cats write all the exams. Okay, last part. Give me this one really fast. Go ahead.
B to the 5th minus a to the 5th over 5 t epsilon naught r squared plus 5q over 4 pi epsilon naught r squared.
That's exactly what it is. Okay, let's go through and see it. Okay, so in this case here, we're way up here. So go my Gaussian like this. Okay, kind of be smart about this. What does that have to become?
So something 4
That doesn't change. Okay. Now, the Q enclosed still has to be the Q of the sphere. This guy here, plus this guy here. That doesn't change. Now, can I use this Q of the sphere as it is here?
No, because you're not going up to r, you're just going up to b.
Yeah, if I use this just as it is, if I use this expression exactly as it's written here, what am I saying? I'm saying that this charge goes all the way up to here and it doesn't. Where does the charge stop? It stops here at B. So you're gonna have this exact same expression, but what's the difference you have to do here?
About
Yeah, this little r here has to become
b.
B. So what I would have is I just have to change this to B. So this has to become 4 pi over 5. B to the 5th minus a to the 5th. As you're charging those, this has to be divided by epsilon naught. Okay. Does that make sense?
Yeah.
That's why. Then we divide through by our little friend. I won't bother to simplify it in this case here, just because I don't want to. No, that's all right.
This will be the case for all of them. Remember, this week on this.
Yeah. I hope there's another part to this.
Is there? Let's see.
Okay, questions of this? But it turns out we're going to surround this object by a hollow metal shell
Oh my god.
of inner radius C and outer radius D.
Who makes those?
I don't, my cats are just crazy.
No, I mean the spheres. Like,
I don't
think
pretend
you
my
could
cats
make
make them
them,
too.
Because it would have to be floating without gravity. Which,
his guys will probably do that.
yeah, his cats are really simple.
They're clever. They're clever felines. Okay, so suppose, suppose the non-conducting sphere is surrounded by a metal sphere of inner radius C and outer radius D. So let's draw a little picture of it. So here's your little 5Q. A, B. We're going to surround this by something with C. And this is D here like this. Metal shell. Okay. I want you to find the induced surface charge on the inner surface. Actually, let's do this. Find sigma induced on the inner surface of metal shell. Proceed. And after this, we will do the infinite plane.
You want the answer?
So what's the definition of sigma? Sigma is, by definition,
Charge your
charge per unit area. Okay. So first of all, why would you have charge induced on this thing here? Let's figure this out.
Because we have the E field coming out.
And so we have electric charge here.
Yeah.
Okay. And this electric charge from this object here, what is it going to do?
It's gonna repulse the no, it's gonna attract the electrons towards it.
Yeah, so let's actually go this thing. So we're going to have these electric fields coming out like this.
It's gonna terminate on something. Negative charge.
Now see a field coming out from this center guy here. And do we have any electric field inside the metal?
No.
No, we don't. So it has to stop here. So what is this going to do? Since this is a metals mean that you can have charges that freely move. Okay.
Negative.
So what's it going to do?
Induce the negative charge.
Yeah, there's going to be a force on the negative charges here moving this way here. And so what's going to happen is that you're going to induce these negative charges here. Okay, so these are induced surface charges. Okay. Does that make sense? So the sigma here is going to be what? The sigma is going to be the Q induced over. And what area is it distributed over?
4 pi c squared.
Yeah, the center sphere here has a radius c. So the surface area of that sphere has to be 4 pi c squared. So now we need the Q induced. So how do we find the Q induced?
From the last problem.
Yeah, we got
Yes.
that from R squared.
Yeah, we know. Come out here some distance like this in R. Construct this Gaussian surface here. This guy. What has to be the electric field inside a metal again?
0.
0. So you get the 0 equals Q enclosed over epsilon naught. So this tells you that the Q induced has to be 0. I mean, the Q enclosed has to be 0. Now, what's the charge enclosed here? There's 3 terms to it. What is it?
5Q plus Q inner
Okay, so this Q closed has to be this 5Q plus
Q of the inner shell and the outer.
yeah,
shell.
the charge of the center guy here, which is what? It's this value here with a B in here. This is 4 pi over 5 e to the 5th minus a to the 5th plus whatever the Q induced is. That's that idea of equals 0. Okay. So our Q induced is the negative one, minus 5Q minus 4 pi over 5 e to the 5th minus a to the 5th. Okay. So that means our sigma is going to be this guy here. All over this guy. That's a very standard thing I expect you to be able to do. I should say my cast expect you to be able to do.
Do we have to prove it all the time like that, or can we say that the Q induced should be negative of the Q?
I mean, I would accept, and on a test, I would accept that. It makes just as long as you understand the reason.
Okay.
Okay. And so that's a fairly involved problem. There's a lot of reasoning there. Questions to that?
What should come to C and C, so panel C is 0, is it 0?
Yeah, because the electric field is 0, so it's.
What is an electric field? Because you have a field
Hmm?
that is electric, so it has to do with electrons, but
Does not happen.
it doesn't have to do
I mean, electrons have electric field, but you can have anything with electric charge will have an electric field around it.
what does it actually mean?
Okay, one thing is it's just a new property of matter that it exists. When you go to, in terms of quantum mechanics, the quantum mechanical theory of electricity magnetism is called QED, quantum electrodynamics. And the way you do it is you basically view all forces as basically you have particles here in the inner exchange where it's called a virtual particle. It's actually due to that particle exchange. And that's actually connected with what these things really are. But at this point, all we're saying is that if we have charge, there's a new property, okay, called electric charge, and this actually has around it an electric field. Okay. And so we go to other things in physics. Let's say we have color. Okay, this is badly named. In particle physics, all the names are stupid. So it turns out that when you have quarks, quarks have a type of new charge, which we call color, which has nothing to do with color. Okay. It turns out there's 3 of them. And so when you have these colored objects, they then have a color field around them. Okay. And so there's kind of an electric field associated with color. So that has nothing to do with color. It's badly named. Questions? Yes.
Does the metal sphere have, does it have to be uniformly charged?
Okay, so does it have to be uniformly charged? There would be if it's
not a
Spherical.
metal.
sphere. If you make this, if you kind of made this all weird, it would not be uniformly charged. But the total charge on it would still be this guy here. But your sigma would no longer be this.
Okay.
Questions? Okay, infinite plane. Okay, this one here, primarily what we're going to do is there's not a lot of problems I can give you kind of along the line of actually doing Gauss's law with this. But the result that we're going to get for this, we're going to use all the time. It's going to become really important when we do capacitors. Okay, so this is the last geometry, the infinite plane. Okay, so consider a uniformly charged infinite plane. So I have to draw a couple little things here like this. So imagine by that, I mean, so here's a plane. Now imagine this plane is infinite. We're going to take charge and basically put it all along here. That it's going to be uniformly distributed. So I draw a couple of views here. So a side view. The side view would be this. In other words, if you're like this, and if here's your infinite plane, if I look like this, I'm just seeing the line. Okay. We want to find E for this. Okay.
First of all, it's gonna be
Tree
more
has
long.
collection of point charges.
You can actually do that, but we're not
And
going to.
then integrate over the plane.
That would actually work. You could do that. Okay. There's actually kind of an easy way to do this. So I'll get to that maybe later on. But what's the other way we're going to do here? And why?
Gauss's law.
Why Gauss's law?
One of the geometries.
That's one of our three geometries. Okay. So we're going to use Gauss's law with this. Now, what's the first step in Gauss's law?
Draw geometry.
Draw your
Gaussian
Gaussian surface with
the same symmetry.
same symmetry is a problem. Okay.
That's tough. Then.
Yeah. What kind of symmetry do we have for this guy?
Central.
Two-dimensional symmetry.
Well, it has to be a closed surface.
But it can't be close. It's infinite.
The Gaussian surface is always closed. Surface can be infinite. Doesn't matter. It's like our infinite wire. We did that was infinite, but our Gaussian surface is always finite. It has to be a closed surface.
Well, the cube wouldn't be good. would
You
it?
could do cube will work. Okay, but how would you have a cube? How would you draw it to make use of the symmetry?
Like so the center plane of a cube would be on this plane.
Yeah. So what you're going to do? You're going to basically have and it doesn't have to be a cube, although I'm going to take it to be a cube. It's going to be like this. So if you actually draw this thing up here, you'd have something like this. This is above the surface, and then this would then come
So same part below this.
below the surface.
It's a magnet.
Whoa.
In other words, we kind of screw up this diagram here. It's like this. In other words, this is our Gaussian surface. So in other words, here's the infinite plane. Imagine that's if I could take this box, this Kleenex box, and put it right in the middle. Okay. That makes sense?
Mhm.
So this is what we have here. Okay. That part's done. Okay. Now what? And again, the distance above here is the same as the distance below here, although you can't tell by my diagram. I gotta make this look a little more uniform.
I would proceeding with a cube if so.
That won't make a difference.
Okay. We can start drawing our E lines and
Okay, how does E have to look?
perpendicular to the surface.
Yeah. Okay. So if I had an infinite plane here, okay, that electric field is going to be coming out like this, straight like that.
And we prove it
Okay.
with any surface. right?
Well, with any infinite surface like that, if it's uniformly charged, it has to be like that. Why can't it be like this?
We proved it, it would move, the electron charges would move.
Okay, it would move, okay, but why can't it still
Oh,
be?
they, mm,
Why can I, if I have a,
they say that they don't cross, the lines get crossed.
okay, so let's say I have an infinite plane length. Yeah. Why can't I just have all the electric field like this?
It would have, electric field and this is a force, and then, on charges.
Well,
And the horizontal component of electric.
all that's true. I'm gonna do it.
Okay.
Ignore it. Okay, why can't it go like that? Everything you said is true. Okay. But give me another reason why I can't. Give you a hint, it's the most important thing you do, one of the most important things you do in physics, symmetry. So to have this, what would you do? Here's your thing like this. I'd have a tiny little DQ here. I have a point here. That would be my electric field. Finish up there. Right. If this is my electric field from the D, so I'll call this DE here. So I have a tiny little DQ here. This little DQ is going to have some electric field here at this point going like that. Okay. Now tell me why. How you go about doing this. What's your other method for finding the electric field?
Integrating.
You treat the object as a collection of point charges and then you integrate it with the object.
Yeah.
Or do you think there's going to be another DQ? Take a look. This is the center part right here, right? This is perpendicular here.
Yeah.
There's going to be a corresponding DQ on the other side here. This is the DQ 180 degrees on the other side. I think there's some redundant.
Would that be like the top right?
Yeah, so in other words, if you were to have,
It's just symmetrical along the axis.
so in other words, if I have this DQ, let's say, here's a center, so I want to find the electric field here. If I had a DQ here. Okay, this would be the corresponding DQ over here. Okay, that's what I mean.
Okay.
Okay. What's going to happen?
The horizontal.
The horizontal components will cancel and you're just going to be left with this part. And that would happen point by point. That's why that electric field has to be coming spit out like that. Okay? That makes sense?
All right, yeah.
Okay. So if you were to draw this guy, this electric field looks like, I think this electric field is red. Okay. Now what? We need DA. How many DAs do we have?
1, 2, 6.
We have 6. Okay. I won't draw all the DAs because they get a little hard to see. Okay, so I can draw a DA on the top. How does my DA on the top?
Upwards.
That's
Outside.
my DA here. Let's do the bottom.
Comes down.
Down. Let's do the side over here.
Right.
Like this. Okay. And then so on and so forth for all the other ones. That makes sense?
Yeah.
Now, when you look at this guy, that's okay. Okay, what does this become? How many terms?
6.
6. So you're gonna get this flux on the top. Flux on the bottom. Let's flux here from the 4 sides.
The sides would be 0.
Correct. Why are all the fluxes on the side 0?
Because they would cancel.
They don't cancel.
The
I don't know.
DA is
The angle.
perpendicular to,
Yeah, for all these here, on all the sides here, if you look at the E's here, the E and the DAs are all perpendicular. So in this case here, E is perpendicular to DA on the four sides. If the E is perpendicular to the DA, the dot product is zero. Good. No, none of the electric field is poking out through the sides. Okay. So tell me what my friend is here. E dot DA on the top. Oh, work it out. So this is your magnitude of E, magnitude of DA. So what angle does Z and DA make on the top?
Zero.
Zero, plus on zero. This is the bottom. Magnitude of V, magnitude of DA. What angle does Z and DA make on the bottom? Tell me why it doesn't.
0.
Why is it zero?
Because
The
DA
E is going down and the DA is going down. Okay. In this case here, it's cosine of zero. Okay, so this has to equal your Q enclosed over epsilon naught. Okay, what can I say about the magnitude of E anywhere on top of here? It's the same, I can pull it out. Then if I take a DA and sum them up over the whole top, what do I get?
the area.
Area.
Yeah, so I'm going to call this area here. I'm going to call that A. I get EA. Plus, now what did I say about the distance above and the distance below?
They're equal.
Okay, so if I call this distance here D, and this is distance is D, what can you say about the magnitude of this E here?
Same as this.
It has to be the same as the top.
So it's 2.
Yeah, so I can pull this E out of here. If I sum up all the DAs on the bottom, I get this area here, which is the same. So this is an EA on the bottom. This is our Q enclosed. So this gives me 2E equals Q enclosed over epsilon. Now, if I just say shade in the Q enclosed, where is the Q enclosed?
The middle, the central plane of the.
Yeah, the charge in here. That's my Q enclosed. If I go over to here, surely this charge right here. That's your Q enclosed. Okay. I divide through by the 2 of the A here. Hey, does this have a name?
Yeah.
That's going to be sigma 4, the infinite plane.
Yeah.
Sigma. There. What is unique about that value? It is a
Constant.
constant. Okay? So no matter where you are, anywhere along here, you're going to get the exact same value of the electric field.
Right. So you mean even if you
That-
go
that makes
farther
sense.
out, if you go farther out from the plane,
If you have an infinite plane,
yeah, infinite plane.
then it will not make a difference.
Okay.
It's entirely due to the infinite symmetry. Now, you don't have an infinite plane, so where would this apply approximately?
Large planes.
Nowhere.
Well, okay, yes and no. Okay, so imagine I had a plane like this, and let's say I put charge on it. I'll explain how you do that later on. This is obviously not an infinite plane. Where would this value though work pretty well?
Close to the surface.
Close to the surface where?
At the center. Center. close to
Somewhere
the
in here. If you're in this range here, that's going to be kind of an approximation for this.
Yeah.
If you get closest to the edge, you're going to get these weird edge effects, and edge effects are bad to deal with no matter what you do. If you go too far away as well. Okay? But if you're in this region right here, you have more or less a uniform electric field. Okay? Does that make sense?
Yep.
Okay. What we're going to do next time, we're going to do the following. Let me just kind of set this up for you. This is the preview for the class. So the preview for the class, okay, I'm going to take a metal plate here. And take a metal plate here like this. And I'm going to connect this to a battery. Here's the battery. Okay. What do you think's gonna happen? First of all, what does the plus sign, what does the minus sign mean on the battery? It's really showing you how the electric field goes. So what's gonna happen here, if I have thick wire here, so I'm gonna make the wire thick. This plus side here really means there's an electric field, and it's gonna be in this wire going this way. There's gonna be an electric field this way, and this wire going to here. So if you were a tiny little negative electron here, which that's the only way you can be an electron, okay? Which way would you go? You're here, you see this force, electric field.
Pushing you to the surface.
It puts a force on you,
Yeah.
moving you where?
Other plate.
It's gonna take the electron, move it this way.
Okay.
It gets to this terminal, the battery, then what happens? Chemistry voodoo, okay? And electrically, chemically, it gets moved over to the side here. You know, I looked at these half cell potentials and stuff like this. That makes absolutely no sense. Okay, fine. Some chemistry magic occurs here. Now your little electrons on this side. Now where does it go?
Was,
The force is still this way. Now you get over to here. What's going to happen to another electron here?
Same thing.
It's going to move over here, chemically take to this side, go over here. What's going to happen? This plate, as it starts losing electron, will
Positive, be positively charged.
become the positive charge. This is going to then become
Negatively charged.
negative. That's what we're going to look at next time. We can do a lot with this. Have a great day.
That? Hey, Rock, did Noam just say that he played volleyball?
Yeah.
How did they do that? Like
I
when?
play too.
You play too? Okay, when and where can you play volleyball? Tell me.